So it's going to be a relatively brief lecture today, I believe, but we're going to cover an entire section of the textbook. It's just a relatively brief section of the textbook, and that's the graph of logarithms. So let's discuss logarithms. We've defined them as a way to rewrite exponential equations. But we can also understand logarithms as functions. Like f of x equals the logarithm base 2 of x. And what this function does, it takes x as its input and gives as its output the number you must raise to the base 2 in order to get x. So, for example, f of 8 equals 3. Because what number do you have to raise 2 to in order to get 8? Well, 2 cubed equals 8. So we can think of logarithms as functions, and we have questions we can answer when we're looking at functions. We can ask about the domain of the function. We can ask about a range of a function. We can ask whether the function has any local extrema. Questions like that. Before we get into it, there's only one person here. Do you have any questions about how we understand logarithms as functions? If not, then we'll briefly, I mentioned before that this is going to be a pretty brief lecture, but briefly but comprehensively discuss the properties of logarithms. So let's start with the graph. If we're given a new function, we are probably interested to know what its graph looks like. Let's go to Desmos.com and let's start graphing logarithms. And let's see if we can find any pattern. So here is the logarithm base 2. Let's zoom out a little and let's see what we can make of this. The logarithm base 2 appears to only be defined in the first quadrant and the fourth quadrant. There's nothing over in the second quadrant or the third quadrant where x is negative. And that gives us a property of logarithms. Let's jot these down as we go. The domain of any logarithmic function is the strictly positive numbers. And why is that? Well, look at this logarithm base 2, for example. Say you wanted to try to define f of -3. F of -3, if it existed, would be the number you must raise 2 to in order to get -3. However, going back to our graph and hiding this for a moment, 2 raised to any number is positive. So here's 2 to the power of x. When does this equal -3? When does it hit this green line? Well, it never equals -3. It never even comes particularly close to hitting -3. So for that reason, no such number exists, and f of -3 is undefined. And it's true that I've made this assumption based on a single graph. But all logarithmic graphs look the same. So here's the logarithm base 3. And it's also not defined in the second or the third quadrant. Here's the natural logarithm, the logarithm base e. It's not defined in the second or third quadrant. The common logarithm, the logarithm base 10. It's not defined in the second or third quadrant. This is a general property that all logarithms have. All logarithms have what we call a vertical asymptote. And again, under the normal circumstances, we'd have already talked about vertical asymptotes because we would already have talked about polynomials. These are not ordinary circumstances. What is a vertical asymptote? Well, you might recall when we discussed exponential functions, we discussed horizontal asymptotes. The idea that we have a horizontal line and the exponential function kind of merges into that horizontal line. Using that as a guideline, here is a vertical line. Maybe this will be easier to look at to see if we get rid of everything except the curves. Here's a vertical line in blue. Here's the curve in red. And you see that this red line and this vertical line merge together down here. So that's what we mean when we say that a logarithm has a vertical vertical asymptote. And the vertical asymptote is always the same. The logarithm merges into the line x equals 0. And that is true even if we change the logarithm. So here's the logarithm base 3 instead of the logarithm base 2. But you see that near 0, the curve in red and the curve in blue are indistinguishable. They both just look like vertical lines. What about, I might want to get this back. Let me bring the axes back. What about the range of a logarithmic function? We talked about the domain. The next thing we talk about, you might think, ought to be the range. Instead, we talked about vertical asymptotes. Notice that vertical asymptotes are related to the domain. This vertical asymptote at x equals 0, 0 is not in the domain. We have an open parenthesis here. We're excluding 0. So the graph seems to merge into this vertical line, but it never actually hits the line. It gets closer and closer, and they become visually indistinguishable, but we never actually hit the vertical asymptote. What about the range? The range is all the real numbers. So that is to say that an equation, let me adjust that so you can see this, an equation that looks like this always has a solution. The logarithm can equal positive numbers, it can equal negative numbers, it can equal 0. The range is all the real numbers. So what do logarithms look like? Well, we've already seen computer-generated images that are going to be significantly neater than anything I can draw, but we emerge with the line y equals 0 as we get closer to 0. And then as we go to the right, we grow. So logarithms look like this. Although I suppose that statement requires, what's the word I'm looking for? A condition attached to it. The logarithm base b of x is always going to look basically like this, assuming the base is, not greater than 0. the base has to be greater than 0. Assuming the base is greater than 1. If we had a base that was less than 1, let's change this 3 to a 1/2. Not having much. There we go. Then we get a different looking graph. However, having just mentioned this in passing, I'm now going to proceed not to worry about it. We can always assume that the logarithm we're looking at does have a base that's greater than 1. I mean, what are the logarithms we commonly work with? The two standard logarithms are the common logarithm, which has a base of 10, and a natural logarithm, which has a base of e. And if you're doing computer science, you could throw in the logarithm base 2 as a third commonly used logarithm. So all of the commonly used logarithms look like this. We don't worry about logarithms where the base is less than 1. So, one final remark about the logarithm that is worthy of some attention. The logarithm is always increasing. That's assuming, which we do assume. We can handle questions about the homework after I finish this then. That's assuming, which we do assume, that the base is greater than 0. But the logarithm is increasing very slowly. Let me just give me a second to get our calculator up on the screen so that I can share it. Here we go. And let's look at a logarithm. Let's go ahead and look at the common logarithm. it has its own button, the common logarithm of x. And I'm going to go to the table. Let me delete all this stuff that was already there. And let's see what the common logarithm does as x gets large. When x is 10, the common logarithm is 1. Because, the common logarithm is 1. Because 10 to the first power equals 10. When x equals 100, the common logarithm is only 2. 10 to the second power equals 100. When x is 1000, the common logarithm is still 3. 10 to the third power is 1000. And you see the pattern. When x is 1,000,000, the common logarithm is still only 6. And we can see that graphically as well if we go over to Desmos. Here's the common logarithm. We zoom out, and let's actually change this. Let's let y just go from 0 to 10. I seem to not be having much luck. Here we go. Let's let y go from 0 to 10. And it's increasing, you can see. But here x is like 3000, and the common logarithm is still under 4. Here we can let x go up to 100,000, and we're steadily increasing. But the common logarithm just reaches 5 at the very end of our viewing window. And as I say, we have to let x go all the way up to 1,000,000 before this thing reaches 6. So it's always increasing, but it's increasing extremely slowly. And many people seem confused about this. You hear people talk about increasing logarithmically when they're trying to say that something is increasing very fast, but that's the opposite of what increasing logarithmically means. If something is increasing logarithmically, then it's increasing incredibly slowly.